Hello, my name is Prayaag. I'm a graduate student at Harvard. Today I'll tell you about efficient algorithms for certifying lower bounds on the discrepancy of random matrices. So here's a brief outline of the talk. So let A be an m by n matrix and define the discrepancy of A to be the minimum over all signings x of the infinity norm of the vector A times x. In this talk, I'll be focused on the discrepancy of random matrices A. In particular, for the purpose of exposition, let's consider the simple model where the entries of A are IID standard Gaussians. In this setting, it's known that the discrepancy of A is equal to roughly square root n divided by exponential and n divided by m with high probability. This is shown by non-constructive means. So a natural computational question associated with this definition is that of discrepancy minimization. Given an input matrix, hey, can we compute assigning x in polynomial time with a small value of A times x infinity norm? So for this problem, it's known that the best polynomial time algorithm can compute assigning achieving discrepancy value, which is roughly exponential and negative log squared n divided by m. So these two results are summarized on this axis depicted on the bottom. This axis depicts various discrepancy values. Clearly, the discrepancy is always non-negative by definition. We know that this middle value of roughly square root n divided by 2 to the n over m is the true high probability value. And the best polynomial time algorithm can compute signing achieving discrepancy value, roughly this second expression. Moreover, we don't know of any algorithms achieving discrepancy values in between these two, even though we know by these non-constructive means that such signings exist with high probability. So I'll tell you 3 reasons why average case discrepancy is an important and interesting topic to study. So first off, it's been studied tremendously for worst case settings A. So it's natural to consider an average case version of this problem. Second, the average case problem is related to covariate balancing in randomized controlled trials and the so-called Ising perceptron model from statistical physics. Finally, this is an example of a problem with a conjectured information computation gap. As alluded to in the previous slide, there's some regime of discrepancy values where we know there exist signings achieving such value by non-constructive means, but we don't have polynomial time algorithms to find such signings. So it turns out that this discrepancy problem is related to something called the planted Boolean vector and random subspace problem. This is a well-studied problem for which there is significant evidence that such an information computation gap really exists. Moreover, in recent years, burgeoning line of research has developed various tools for reasoning about these information computation gaps. That is to say, these gaps are inherent and not due to a lack of creativity on the part of algorithm designers. Unfortunately, these tools are generally ineffective at reasoning about average case discrepancy problems. So in order to shed further light on this issue, in this work, I propose study of the following certification problem, which is as follows. So the goal is to design an efficient algorithm which on input matrix A outputs a value alg of A, which satisfies 2 properties. So the first property is that for every input A, the value output by the algorithm is a faithful lower bound on the discrepancy of A. The second property we wanted to satisfy is that for random A, for example, IID Gaussian entries, alg of A should be close with high probability to the true high probability value of discrepancy of A, which we know by non-constructive means. So I'll just give a few remarks about this problem. So note that the trivial algorithm for this problem just outputs the value 0 for every input A. This clearly satisfies the first property, but it's not very interesting because it doesn't satisfy the second property. So we are interested in designing algorithms which satisfy this first property, but output a value that is positive with high probability. The second remark is that worst case version of this problem is like a co-NP problem. That is, we want to determine, or we want to prove that a given matrix has a large discrepancy. That is, there does not exist any signing achieving a small discrepancy value. Note that this is a highly non-trivial task because the trivial algorithm for proving that no such small discrepancy signing exists would amount to enumerating the 2 to the n possible signings and computing the discrepancy value achieved by each of them. So if we have an efficient algorithm for this problem, it's interesting because the algorithm, or the output of the algorithm, is itself a proof that the discrepancy of A is large. This is in contrast with the discrepancy minimization problem, where proving that a matrix has a small discrepancy is simple. One just needs to exhibit a signing. The third remark I'll make is that if we can solve this certification problem, we can immediately distinguish this distribution of random matrices from any other distribution on matrices which have a strictly smaller discrepancy value. In contrast with prior work, we don't study the search version of this problem, that is, finding an actual signing. In general, the search problem and the certification problem are not relatable, and their complexities can be quite different. Now I'll give you 3 reasons why the average case discrepancy certification problem is an interesting one. So the first, I'll mention a relevant fact, which is that it turns out semi-definite programming-based algorithms fail to certify any non-trivial value. That is, with high probability, an appropriately defined semi-definite programming value is just equal to 0. This is notable because for many average case problems, we believe that semi-definite programming-based algorithms are optimal among polynomial time algorithms. So the fact that this powerful class of algorithms fails to do anything non-trivial, and we don't know any other algorithm, is itself very interesting and peculiar. The second reason for studying this problem is drawing inspiration from this beautiful work of Feige, Kim, and Ofek, who studied the problem of refuting random k-set formulas. As mentioned, a worst case version of this problem is some type of co-NP problem. It was very natural to study an average case version to try to understand, at least at a very informal level, relations between complexity classes like P, NP, and co-NP. Finally, there's a very rich literature on refuting random constraint satisfaction problems using semi-definite programs. The fact that semi-definite programs fail for average case discrepancy certification gives us an opportunity to potentially inspire and design new algorithmic techniques that can surpass STPs for some class of interesting average case problems. So these are the 3 reasons why average case discrepancy certification is an interesting problem to study. So I'll now tell you about the 2 main theorems of this work. So the first theorem states that there exists a deterministic polynomial time algorithm that on input matrix m by n, which has IID Gaussian entries as before, with m smaller than n, the algorithm certifies that the discrepancy is bigger than the value exponential and negative n squared divided by m with high probability. The second main theorem states that if we relax deterministic polynomial time to non-deterministic polynomial time, we get an algorithm which can certify an improved value, that is exponential and negative n log n divided by m. So here, non-deterministic polynomial time algorithm for the certification problem means that there exists a polynomial time verifiable certificate that the discrepancy of A is larger than this value, but it doesn't necessarily guarantee the existence of a polynomial time algorithm to find such a certificate or witness that the discrepancy is large. So I'll summarize these two theorems and our sort of knowledge about the average case discrepancy problem in the following figure. Again, I'm depicting this axis, which represents discrepancy values. The trivial lower bound is always 0. We know that this third expression here expresses the true high probability value of the discrepancy. We know from prior work that for discrepancy values larger than this fourth expression, there exist polynomial time algorithms to find signings achieving such discrepancy value. The main contribution of our work is sort of on the lower bound side. So the first main theorem states that for discrepancy values smaller than this first expression, there exist polynomial time algorithms to certify that the discrepancy is at least that large. Moreover, if we relax to non-deterministic polynomial time, we can improve the exponent n squared over m to n log n over m. Finally, prior work and the current work leave this middle regime open. I'll discuss more about this later. I'd also like to translate these results into some very non-rigorous and informal complexity theoretic language to shed a different perspective on it. So we know that the problem of the associated decision problem to discrepancy minimization is in NP. We know that the associated worst case decision problem of discrepancy certification is in co-NP. The polynomial time search algorithms from prior work state, roughly speaking, that with respect to the complexity of this average case discrepancy problem, NP is contained in P for discrepancy values larger than this fourth expression. Our work states that, again, informally, that for discrepancy values smaller than this first expression, co-NP is contained in P for this improved discrepancy value given by the second expression, co-NP is contained in NP, and then in this middle regime, we don't know any non-trivial statements. So now I'll give a few remarks that put this main theorems in context. As mentioned, these are the first non-trivial algorithms for average case discrepancy certification. They outperform semi-definite programs, which is notable example among many average case problems for which semi-definite programs are actually believed to be optimal. Second, as a corollary of our main theorem, we give a polynomial time algorithm for what's called the detection problem in the negatively spiked Wishart model in some regime of parameters for which we neither knew algorithms nor hardness results. As alluded to in the previous slide, our results raise the possibility that the landscape of the average case discrepancy certification problem actually resembles quite closely that of refuting random three-set formulas in the unsatisfiable regime, as established by this work of Feige, Kim, and effect. That is to say, there's some regime of discrepancy values for which there are polynomial time algorithms to certify the discrepancy is at least that value. There's an improved regime of discrepancy values for which there are polynomial time verifiable witnesses that the discrepancy is at least that value, although we don't have algorithms to find or compute those witnesses. And finally, there may be a regime of parameters where there do not even exist polynomial time verifiable witnesses that the discrepancy is larger than that value, even though we know by non-constructive means that no such signing achieving those discrepancy values actually exist. The final interesting feature about this work pertains to the techniques which involve a reduction to the so-called shortest vector problem on lattices. So there's been a recent line of work which demonstrates that these lattice-based techniques are able to surpass STPs for certain average case search problems. So the present work complements this recent work by demonstrating the utility of lattice-based techniques for solving certification problems as well. I'll now give you a brief overview of the main techniques behind the proof. So our starting point is the following observation. So consider the polytope S sub delta, which is defined to be the set of all vectors X, so that the discrepancy of X is smaller than delta, and the coordinates of X are bounded between -1 and 1. So observe that this polytope contains all low discrepancy signings, if any exist. However, it contains also spurious low discrepancy. It potentially contains spurious low discrepancy signing. This leads us to the conclusion that if the set S delta contains no non-zero integer point, then we may immediately conclude that the discrepancy of A is bigger than delta. So this gives us an algorithmic approach to certifying that the discrepancy of A is bigger than delta. We simply need to certify that the set S delta, which depends on the input matrix A, does not contain a non-zero integer point. However, in general, these kind of problems are known to be very hard. So we need to relax in some way to a lattice problem that we can hope to solve efficiently. So to this end, one of the tools we use is an algorithmic version of something called John's theorem. This guarantees the existence of an invertible linear transformation T, so that if we apply this T on the polytope S delta, we can sandwich the transformed set in between an L2 ball of radius 1 and an L2 ball of radius square root n. So given this sandwiching, we can immediately observe that if we also transform the set of integer points in Rn, we intersect that with the L2 ball of radius root n, and the intersection contains only the zero vector, we may immediately conclude that the discrepancy of A is larger than delta, as desired. So now let's consider the statement of this intersection being only the zero vector. It turns out that this linear transformation applied on the set of integer points is an object called a lattice. So basically, this problem boils down to determining whether a given lattice, which depends on the input matrix A, contains a non-zero vector whose norm is smaller than root n. So if we can determine whether or not this so-called lattice contains a short non-zero element, then we can solve the discrepancy certification problem. And it turns out that this former problem is exactly an instance of something called the shortest vector problem on lattices. As mentioned, this is a hard problem to solve exactly. So one of the key technical challenges that we surmount in this work is to demonstrate how to use an approximation algorithm for SVP to solve this discrepancy certification problem. It turns out that the approximation factor of the algorithm used for this shortest vector problem can be translated into the discrepancy value delta that is certified in the end. So to summarize, the main contribution of this work is that we introduced the problem of average case discrepancy certification. We gave the first non-trivial algorithms which surpass the performance of semi-definite programming-based algorithms. And the state of affairs for this problem is summarized by this figure I discussed before. So, as hinted at by this figure, one of the main open directions is to try to understand whether these gaps are inherent or there are actually algorithms which can close these gaps. Another interesting direction pertains to reasoning about the limitations of lattice-based algorithms. So even though we demonstrated that lattice-based algorithms can surpass STPs, unlike STPs, we don't know how to exactly reason about limitations of this class of algorithms. Finally, it would be very interesting to understand whether there are more average case problems for which these lattice-based algorithms can surpass STPs. The current work has added one such problem to the list. It would be very interesting if we can get a more thorough understanding of the class of problem for which this phenomenon occurs. I'd like to acknowledge these funding sources and thank you for your attention.